Hello and welcome everyone. In this day 35 learning, we are going to be looking at searching linear, binary, and string searches. So, we have just completed the sorting uh, algorithms in past three videos. We started off with bubble sort, selection sort, insertion sort, and the next day we looked at merge sort, quick sort, and at the last we looked at linear searching algorithms along with shell and heap sort. Right. Today we are going to be understanding searching, which is also going to utilize some portion of sorting in one or the other way in order to make searching easier. So know that sorting, um, there are multiple algorithms and they can be used in combination. Like for example, a uh, can be linear search algorithm can be implemented on an unsorted array, which simplifies the array much better, like a radix sort or a bucket sort. And then the linear linear sorting applied filter array would then be processed to maybe a merge sort or a quick sort to have a much better time and space complexity, right? So, but yeah, let's start with linear searching algorithms. So, first thing is we have linear search. So, let's say we have uh, linear stands for one by one. Let's say we have an array of 10, 25, 7, 30, and 15. So we have a target of search 30. So the way that we do it is we iterate through the array and check if this is present in the array, right? So there might be a for loop I to array length, and of I is equals to target return else exit and return false, right? No for something like this, right? So let me quickly switch to JSPin editor and let's quickly walk through this code snippet. Okay, so linear search. So here are a few things. So yeah, this is a linear search, and there are two variations that I have here. One is linear search for a single target, and if there are multiple occurrences of a target, then we use this, right? So that's the whole idea of these two functions here. So first thing is, let's say we have a for loop. If there is I return one or true, then we return minus one, right? So that's the whole idea. And next thing that we have here is, okay, so the next variation here is linear search all, where we iterate and we push all the indices of the target occurrence with respect to index I, and we return the indexes like here, right? Yeah, so that's the whole idea. So here we were searching for minus one, or we were searching for 5, which 3, which occurs at index 1, 3, and 5, right? So that's the whole idea. And if there is no occurrence, then we return minus one. Okay, so that was about it. Let's, as you can see, there is a power off in my background, so you might see my background a little blurry. So yeah, uh, let's switch to binary search, and let me keep this video very short in nature, right? Switching back to drawing board. So second one we have here is binary search. So in binary search, So array is always going to be split into half. So we have a low and high pointer. So and we calculate a mid value, and prerequisite here is pre-sorted array. So let's say we have a value 2, 5, 8, 12, 16, and 23 and 38. So let's say we want to find a value 23. So we know that the mid value here is this one, and we check if target is greater than mid, then move low to mid, low to mid, and recalculate recalculate mid, and then we again find out, uh, let's say we end up with this array 12, 16, 23, and 38, and we find for mid is equals to here. So we calculate low is greater than plus 1, so we ignore this and we calculate mid here, and this would give us the target array. So that's the whole idea, right? So yeah, the way that this algorithm looks like is we would have a while loop, low less than or equal to high, and calculate mid, and once we have mid, then we check if mid is equals to target, return true, return true, else if target is greater than mid, low is equals to mid plus 1, and else we put high is equals to mid minus 1. So that's the way this algorithm goes, and this has a time space complexity of um, n log n, or n by 2, right? Every time the array decreases by size by 2, and here we have time complexity of n. So let me quickly switch to the JSPin editor and let's quickly walk through the code. So here in JSPin, let's look at the code for binary search, low, high, and we have a while loop mid. So if array of return mid, which means we have found the target. If array of mid is less than target, um, so the values are on the left side. So we move the left, array of mid or target is greater than array of mid, we move low value to mid plus 1, and high else high value to mid minus 1. So that's the way, and return minus 1. Recursively, um, we reduce the array by half, like mid plus 1 and mid minus 1. That's the way we use binary search in recursion, right? So that's about binary search, and the time space complexities here. Linear search, if let's say a value is found at the beginning, then we would have often, else often, and space complexity often. Binary search, it would be log n, and one in the worst case log n and often. Okay, so let's quickly look at string search, or a naive way of string search, and then let's close this video out. Okay, let's say we have a strings. Let's say we are given with a string like um, a b a b a b c, and we are required to find a b a b c, this pattern right here. So the way that we do it is we iterate through each character of string, and we also would take in the pattern. Let's say we want pattern, and let's have for loop I to main string, and a while loop, while loop which runs j to 0, j less than pattern length, and text I plus j is equals to pattern of j, right? So if we are having to see um, the input string and the pattern characters match, then we continue testing with it, and we work on it. Else, if j is equals to pattern length, we return true, else false, else false. So the if there is pattern in the string, then the j value will also be equal to pattern length, and we return true, else false. So that's the whole idea here. Let me quickly switch to JSPin and let's quickly walk through the code snippet. So we are looking for a pattern like a a b a b a, which is something like this one here, or maybe even pattern something like here, right? So we have occurrences 0, 9, and also 12, right? So yeah, uh, we have matches array, and we start out with j is equals to 0 and j is less than m, and every time we find a match we push the starting index here, else we return the number of matches. Else we can understand if matches array is empty, then it's a no pattern match, right? So that's the whole idea, and it's n into m, n being the size of the input array, m being the patterns array, right? Okay, so there is one last thing that I wanted to talk about. uh, we know about hash tables or set, uh, hash table search. So for example, we have an array 10, 12, 1, 3, 7, 23. So let's say we want to find 7. We move this to an hash table with objects like 10, 12, 1, and we mark their indexes as 0, 1, 2, and 3 being at 3, 7 being at 4, 23 being at 5. So 1, 2, 3, 4, 5. So let's say we want to find 7, we quickly can return 4, which is O of n time complexity with hash tables. So that's the whole idea. Even though I do not have any code snippets, just wanted to bring this topic out here, right? So that's about it. Let me stop this video for now. So as you can see, binary search requires a sorted input array, right? So yeah, we can be little creative with using sorting algorithms such as linear sorting algorithms such as radix bucket or um, the counting sort, and then use it in combination with merge or q sort, uh, and then bring out a sorted array to pass through binary search and get a faster searching, right? So that's about it. Hope you found this video helpful. Please do like and subscribe to my channel. Thank you.